Hello, everyone. I think it's time now. So, well, since not everybody's here, I will not wait. Okay. Welcome to the PDE course for session 4. I'm your instructor. I'm Xiaoqian. And I hope you will enjoy this course for this semester. It's a math major course. It's a math course, and it's not very easy. Well, although it's I cannot make it too hard, but it's not as easy as a math course you've taken in your first year. But well, this course somehow is very, in some sense, is very interesting. And by the way, I'm also, well, my research area is PDE. So I think this area is quite cool. And by the way, so everybody can hear me, right?
How many people we're supposed to have in class?
Excuse me?
How many people we're supposed to have in class?
I think we will have 12 students, so which means we are missing one at this moment. So
Somebody joined right
now. Yes, we have totally participants 13, and I have 2 accounts, so we need to have 1 more student, but it's okay. Yeah. Anyway, we will record our course, so if anybody misses it, you can still watch it after the course. Okay. So first of all, by the way, so again, I will say this again. I would like to encourage you to open your camera so that we can see each other. That will be slightly better. Yeah, but it's not a requirement. Okay, so if you want, you can open your camera. That will be slightly better, so that I know that I communicate with people, not some pictures. But anyway, it's up to you. It's up to you. Okay. So let's try to first of all talk a little bit about our course. Okay. So this course is partial differential equation. Here are the basic information of this course. We will have our lecture 3 to 5:30 Tuesday and Thursday. And by the way, this is some time block that I would prefer. If anybody of you who have another preference and have a good reason, please let me know, okay? And we can definitely change it as long as everybody agree, okay? For me, it works for me better, but it's not necessary to have this time, okay?
Wait, sorry, so office hours are what days? Wednesday and?
Wednesday, it's almost the same as last session. It's Wednesday from 11 to 12. And well, and each time after class, I will also be here for half hour.
Oh, okay.
And again, if you have another opinion and you would like to suggest me to change anything, because this is online course, okay? This is online lecturing. So if you have any suggestion, let me know, and we can determine whether we would like to change it or not, okay? It doesn't matter because we only have like 13 people in our whole class, including me. So as long as everybody agree, it doesn't matter, okay? We can change whatever you want, as long as you get agreement with anybody else, okay? There's no university's rules about this kind of time slot or whatever. Okay, and for our course, we basically use 2 textbooks, okay, these 2. And the third one is slightly more complicated, but it would be a very good reference. Okay, and we will use we will mainly use, since we are PDE course, we will mainly use the Walter Strauss textbook, which has a republished version in Chinese for Chinese publishers, so you can buy it from Taobao or Jingdong or whatever. And it's not very expensive. I think I bought it around 80 yuan something. So it's not very expensive. And I would recommend you to buy it because this is a good book. And as I mentioned before, Walter is a nice guy. It's pretty nice. And he's also a very good advisor. He has a lot of very, very good students who are very active in the PDE area. And a lot of his students are even Chinese. So I think he's very friendly to Chinese people. So yeah, I would recommend you to buy this book. And now this book, I think it's also written and very carefully and very readable. And for the second book, this is not really a PDE book, but it's actually so-called the Fourier analysis, or someone call it the harmonic analysis. It's a harmonic analysis book. And this book is written by E.M. Stan, okay? Stan. This Stan, he's a professor in Princeton. And he's really an established guy. Unfortunately, he passed away, I think 2 years ago. Well, very sadly, he passed away 2 years ago, so you will not be able to see him again. But he is really established. Of course, he's a very good mathematician, that's for sure. But not only a great mathematician makes him established, he's also a well-known good PhD advisor. Okay, he might be the best PhD advisor in the area of analysis, or at least harmonic analysis. The reason is, his student, he has two very famous students. One, you may not know him, whose name is Charles Feferman, and he is a Fields medalist, and he's a very great, very, very great mathematician. He's now also in Princeton and in charge of, I forgot whether he's in charge of S or not, but he's very great, he's very famous, and he might be one of the greatest guy in harmonic analysis in this decades. And another student, you might know him, another student of Stan is Terry Tao, and he's quite famous as well. He's also a Fields medalist. And the reason, I guess the reason why he is very famous is because he's very handsome and very young. And I think, I don't know whether you know him or not. Tao Zhexuan, very famous guy. And he is also his student. So in some sense, when you try to choose a grad school in US and you are interested in analysis, one of the key factor might be one of the key factor might be you can try to count how many STEM students in that department, and the more it has, the better analysis group it will have. Okay, so which is why I say, well, Stan is really a great guy and one of the best PhD advisor in this decades. Okay. And his book, this Fourier analysis, this book, it's a very good book. It's very nice, and it might be it might be the best math textbook I've read. Because it's really fun and it's not very hard to read for this textbook. Not very hard as a math major student, but it's not like as what he said in this This book, he said that this book is mainly for the non-math major student, but it's really for math major student, so not non-math major student. But this book is very nice. It introduces everything, well, everything that are interested in Fourier analysis. And you'll find that, well, if after you read it, you'll find that Fourier analysis is everywhere and you may feel love with the Fourier analysis, okay? And so we will introduce PDE by Strauss book, the Walter Strauss book, and maybe we will, not maybe, we will try to introduce something because we will need that, something about Fourier analysis by Stan's book, okay, on the second and third week of this semester. Well, and also for this, well, Evans book, this book is also very, well, important in the sense of PDE. If you try to study PDE in your grad school, then you have to read this book, okay? It introduces a lot of basic idea and the basic area of PDE. And moreover, it's very classical in the sense that it's well, it's not so hard, okay? It doesn't use a lot of very advanced tools, but it's every tools he used are necessary for PDE guys. So if you are interested in PDE, you will need to read this book, okay? And also, well, as a math course, those websites are always very important because whenever you see some new terms and you are not quite familiar with, try to Google it and try to use Wikipedia to understand it better, okay? And also, this Wolfram Alpha is a website that's so useful so that you don't really need to open your MATLAB and you can do something, especially in the area of ODE, okay? You may try to ask Wolfram Alpha to help you to solve some ODE. Not necessary, but sometimes it helps. Okay, so basically, this course, as I mentioned before, is a PDE course. Some of you, I guess maybe most of you have taken the ODE course in last session. And you may have some idea about what is a differential equation and what can we do about a differential equation. Like how can we solve an ordinary differential equation and how can we do some analysis about the ordinary differential equation. In some sense, PDE is just slightly more than ODE, which is in ODE, you just solve a function with one variable. But for PDE, it's a differential equation with a function that depends on more than one variable. Okay, we'll see that more. We'll write down the rigorous definition very soon. But you may find that eventually, well, the PDE and ODE are totally different. Although some basic idea like how to solve some very basic ODE, this kind of method, some very easy method, could be helpful when you try to solve a PDE. But soon you will find that, okay, eventually it doesn't help at all. PDE and ODE are totally different. So even if you are not quite good at ODE, don't worry, you may be good at PDE. Yeah, it doesn't matter. It's not really relevant. And moreover, in the sense of ODE, you may find that, okay, well, it's quite normal that you are able to find an explicit solution to an ODE, right? And you always try to do that when you see an ODE. But in the PDE course, the problem is if you want to find the solution to a PDE, partial differential equation, then, and you find a solution, an explicit solution with a formula, then you must be very, very lucky. Because eventually, after this course, you may find that, well, most of the stuff we've learned in this course are theoretical, which means you cannot really use a method in our course to find some explicit solution to a PDE. eventually you will find that most of the PDEs we learn in this course are not something solvable in the sense of ODE. But in the sense of PDE, we still call them solvable as long as you can prove the solution exists. Not to find a solution, but you can prove the solution exists in some sense. Then you're done, okay? So you have to change your mind from solving a PDE, a differential equation, to find an explicit formula, to something that finds the existence of the solution, okay? This is something not very intuitive, but you have to have this kind of idea in your mind, okay? And of course, since it's not possible to find an explicit solution, well, sometimes to find the approximation of the solution is also important. But this would be something in numerical analysis and the numerical method to find the approximation of a solution to a PDE. This is something we may not have time to introduce, okay? So you may need to take some more advanced course in the sense of really find a solution to a PDE, okay? Find approximation of a solution to a PDE. And for this PDE course, again, it's also different from the abstract algebra. For abstract algebra course, maybe some of you I know you took the abstract algebra course, and you will see that okay how mathematicians deal with this this algebra problems. But PDE course is another kind of thing. For PDE course, is well, or maybe I should say for math. In the modern math, the problems of modern math, someone say that always comes from two areas or two directions. One is the number theory, okay? In number theory, you find, okay, there is a problem that you are not able to solve. For instance, the Fermat's theorems or this Gold-Bach's conjecture, those kind of things. You are not able to solve, and it's very easy. So you try to solve it, then you find that it's impossible for you to try to solve it by the elementary method of mathematics. So you have to introduce more tools, more terms, and even more areas to help you to study it. So this is one source of the math problem comes from. And based on this source, we have those kind of algebraic method. Another source of the problems of mathematics is physics problem. For instance, how can you describe those fluid? How can you describe the motion of the water? How can you make the airplane fly on the air, right? How can you, for instance, describe those kind of population problems? Those kind of problems are from the daily life, and we see that those problems are mainly physics problem. Okay, so this is another source of problems that can ask mathematicians to build more tools or to do some study about. This is physical problems. Okay, and for this PDE course or analysis course, they are mainly focused on those kinds of problems. So most of the problems in PDE, you'll find that it has a physical background. And as long as you have a physical intuition, you will have a better understanding of the problems. Okay. And about this course, as I mentioned in the last session, but some of you didn't take my abstract algebra course, so I would like to mention it again. That is, well, how you should learn a math course. Okay. Well, if it is face-to-face, I would recommend you to write down your notes. Although I will share my notes, well, I could share my notes, but I will still recommend you to write down your own notes. Okay, because for my course, I always want to do some lecturing. And if I do some lecturing and you try to learn something, then it's very easy, well, especially in the afternoon, it's very easy to fall asleep, okay? So one reason for you to write a lecture notes would be, it will keep you awake in the class, okay? Which could be better for you in the sense of taking a lecture. And another reason I recommend you to write down your notes is, well, when you try to learn some math, when you try to learn something really theoretical, then one of the best way, for me, I think one of the best way to learn it would be you try to do some, well, try to copy down something on your textbook, okay? Even though there is a textbook, you can read it and you can read it a lot of times, but sometimes when you try to write it down, it will make you feel different, okay? So whenever you try to read some theorems and you try to read the proofs and you read it again and again and you find it's very hard, still very hard for you to understand it, maybe you can try to copy it down, write it down for yourself, and then you may get different feelings about the proof, about the theorems, okay? Again, this is just something I recommend, and well, I will upload, well, not upload, I will share you the link of the videos of our lecture. I will also share you our lecture notes, well, after the lecture. So if you don't take your own notes, it's totally fine, but I would recommend you to do, okay? That's something helpful. And also, another thing is, I would recommend you, if you have any problems, questions in the class, feel free to ask, okay? We only have like 10 people here. And there's no reason for you to feel shy, okay? Don't be shy. And you will know that since we only have like 10 people or maybe 20 people in math major, you guys will be familiar with each other a lot in the next 2 years. So yes, and if you do feel anything that are not quite clear in the class, feel free to ask. Just unmute yourself and ask and break me, okay? Don't need to raise your hand, don't need to do anything. And also, this is a reason why I would like to give the, well, synchronous well, lectures. It's just because I could definitely record everything and upload it and then ask you to watch. But, well, that definitely will not be better than to have a face-to-face meeting. The reason is you can give me the feedback, I can give you the feedback immediately, right? So try to communicate with me in the class. That will be really helpful. That will be the difference that will be the key difference between our course and for yourself to watch the video on the whichever website, okay? So try to communicate with me whenever you have questions, okay? And about the homework. Again, this is a math course. So of course, if you do want to discuss the homework with your classmate, it's totally fine. The only thing I ask you to do is whenever you discuss the homework with your classmate, please write down your classmates' names on your homework. Okay, this is about honesty. Okay, I'll not take off any point from it, but this is a good habit. This will help you to know, well, to remember about the citation. Okay, please do that. And this is our course outline. I didn't write it very carefully. Well, I just write something very brief here, but the thing, well, I may change them. I may change them a little bit, but this is a basic structure. Okay, and don't worry about, well, which section or in our textbook we are cover or this kind of questions. Don't worry about that. You will see which sections we covered by doing your homework. Okay, I will I will mainly assign your homework on the section that we cover in our textbook, either Walter Strauss or Stan. Okay, so as long as you did some homework problems on this section, you know that we have covered this section. Other than that, I will not assume you know. Okay, other than the sections we did homework problems, I'll not assume you know. Okay, so don't worry, don't be confused about which section we cover. Okay, I will only assume you know all the sections that are assigned homeworks. That clear? Okay, that clear? And for the midterms, I finally decided to be on the Monday of the 4th week. It will test you about those linear equations, the characteristic method, and also something about Fourier analysis. Okay, for finals, it will be on the last day of our class.
Sorry, but we have ODE like exam every Monday.
Every Monday.
Yes, 7 in total.
Yeah,
Okay.
we'll have 7 exams for not ODE, real analysis. Maybe.
Yeah, I know. The
Real analysis.
Yeah. Okay, then I can make it on Wednesday. So let's change it on Wednesday. Okay, that's fine. The only problem is on Wednesday. That means you may have slightly more well content that I will test. Okay, maybe slightly more things about the Newton potential or green functions. Slightly more. Okay. Anyway, so this is the standard curve of this course, and in our universities, well, this is well what they recommend me to do, and I'm not going to change it. Although I don't really like this kind of curve, but they asked me to do that, so I will do that. Okay, this is basically the curve, very standard. And if you have any reason that that you want to postpone the midterm or finals or homework, let me know, okay? Let me know before the deadline. This is very important. Let me know before the deadline. Otherwise, I may give you some penalty well, to the school. At least some penalty. Most of the case maybe will be counted as 0, okay? Especially for the exam. If you do have something emergency about the exams, you are not able to do that, then let me know. Okay. By the way, for the exam, please notice that in this semester it is different from abstract algebra. You have 4 hours exam. The reason is, well, this course is not it's not a Hua School student, it's Hua School's course. So I'll not give you unlimited time for this course for the exam. Different course, and for the exam,
course.
Well, yeah, for the exams, you are able to check whatever you want, but you are not able to search the internet. You are not able to communicate with each other when you do the exam. Okay, you can take your textbook, you can take your own notes beside you, and you can check your homework if you want. But you are not able to talk with each other. Okay, you will have to sign the honor score about it. And for the homework, it will be assigned on each Thursday, and it will be due on Thursday's lecture. So it will be due on Thursday, 5:30 every week. We will assign the first homework this week. Okay, and it will due by next week, next Thursday. And as always, maybe you have heard about this. If you are able to submit your handwriting homework, that's totally fine, but you have to make it as a single file. Okay, it's better to be and I would recommend you to make it a single PDF file. Okay, everything, either it is homework or midterms, it has to be one single PDF file. That will be easier for me, and it will be easier for you. Okay, and this will be a very common rules in math department in US at least. We only communicate with PDF file, not other thing. And you could type it, but if you type it, you have to type it in LaTeX, not Word, not Office, okay? You have to type it in LaTeX. I will not accept the Word, the homework typing by Word, okay? And since it's very time consuming, so if you would like to type it in LaTeX, it's optional. It's actually bonus thing. If you like to type it in LaTeX, by the way, it will be harder in this semester to type because you will have a lot of equation in this semester. If you would like to type it in LaTeX, you get 1 point each time as additional point to your final grade. Okay, so final grade, you can see that the final grade, for the final grade, your homework will count as 30 points, and midterm will count as 30 points, and final will count as 40 points. And if you type it, you can add 1 additional point each time you type it by LaTeX. Okay? I think that's clear enough. Is it? So that's the basic rules of this course. Any question about the rules of this course? Any question? And by the way, since these 2 textbooks is not really textbook in our course, well, I forgot to mention because eventually our library say that this book, which I assume it to be our textbook over this course, is out of print, so they are not able to buy it. So these 2 books, I will not assume you have, okay? I will not assume you have these 2 books. You don't really need to buy them, so which means, well, I'll not assume you have them. If I assign any textbook, any problems in those textbooks, I will scan them for you, okay? But still, well, since these 2 textbooks are very nice, so I recommend you to buy them, but this is not a requirement, okay? Any question about this course? Any questions?
So final weight's like 40%?
Yes, final 40% and homework and midterm both 30.
Because I don't know how you guys did on your final for like abstract algebra, but like I think when a final weights for like 40%, it does really kind of drop your score.
Well, but as far as I can see, you guys are all doing well for the total course, for the total grade, right? Although the final, I graded slightly strict, but eventually you guys are all doing very well. Okay, any other question? Any other question? Okay, so if no more question, then let's try to start. Okay. Okay. So this course is so-called the partial differential equation. So what is a partial differential equation? What is a partial differential equation? This is actually a very easy question as long as you know what is a differential equation, right? You have seen a lot of ordinary differential equations in ODE course. If you haven't, that's totally fine. It basically tells you some functions, well, we know the derivative of these functions has some relation with these functions. For instance, the derivative of a function is the derivative of this function is equals to this function itself. Then, well, what can we say about this function? Or what kind of formula we should get for this function? I think in your Calculus 1 class, you probably say that, okay, that this f is a function in t, then f has to be of the form e, well, c times e to the t, right? So this kind of thing you have to know. So basically, a differential equation is like this. It's like you do have an equation which involving an unknown function and maybe the derivative of this function. And then the key part is you want to find this function. Okay, so which makes it a problem. As always, we always call this f to be the dependent variable for the function, and this t to be independent variable. And a differential equation or a partial differential equation, maybe I should say a differential equation is you gave me some relation between these function's derivative and well, this dependent variables relation and the independent variables relation. For instance, well, it can be right as, well, for instance, u equals to u x comma y is a two variable functions. Then we may have some very weird multivariable functions, capital F, such that if you plug in xy, u xy, and ux xy, and uy xy, or in some other notation, x comma y, u ux, uy equals to 0. Okay, this would be seen as a partial differential equation because on this equation, it has the derivative of x and it also has the derivative of y. Okay, or it has a derivative of u and it also u depends on two variables. Either way, could be seen as a partial differential equation. As long as you have a multivariable functions and you find an equation about these multivariable functions involving the derivative, and then we can call it a partial differential equation. Okay, and then we say that the order of a partial differential equation is the, well, highest derivative in your equation. For instance, if you have this kind of differential equation or partial differential equation, you only take one derivative of u. Then it is so-called the first order. First order PDE. Okay? Or, for instance, you may have another equation, say f x comma y, u and ux, uy, and uxx, uyy, and uxy equals to 0. The highest derivative that are in your equation is the second order. You take the second derivative. This is so-called second order PDE. Okay, which is very intuitive. You just count the highest derivative that are in your equation. Okay, and before we go to the rigorous definition of PDE, let me show you several examples so that you will get an intuition about, well, what kind of things are so-called the PDE and well, how far we can go if we really want to solve an PDE. For instance, you may have a function that depends on two variables. And you may have this function. Well, for instance, you know the information that if you take the derivative of the first variable of this function, you get 0. Okay? Then this is an PDE. Okay? This is actually a partial differential equation, although it only involves the derivative in x, but this is a multivariable functions. So we can also call it a PDE. It doesn't matter. But then the problems becomes very simple, right? It's almost like an ODE, right? How can you solve this UXY? How can you solve this UXY?
By integration on both sides.
By finding the antiderivative of this guy in x and this 0, right? If you find the antiderivative, which means you take the integral from 0 to x or 0 to t, or in terms of x, then what you find that is, okay, ux, right, should equals to some constant. But be careful here. This is not really a constant. You take the antiderivative or the indefinite integral, then you should get a constant. But now, this function depends on two variables. Okay, so that constant, it is a constant with respect to x. Okay, so which means it may not be a constant with respect to y. Okay, so when you try to do a PDE problems, this kind of issues may occur, right? So this is somehow different from the ODE. So you can definitely do it again, right? You can find the antiderivative both sides of this equation and then to see, okay, then that means, okay, if you take the antiderivative both sides of this equation, what should you get? What should you get?
It's like fy be the multiplier of x and another like gy.
Yes, that's right. So remember, this fy is basically like a constant, right? It's just a constant with respect to x. So if you take the antiderivative in terms of x, you should get this term plus another constant with respect to x. So it's gy. So if u does not depend on x and y, the general solution to this ODE, should be c1 times x plus c2. But now what you have is c1 and c2 may depend on y. Okay, so this makes the problem slightly harder, just slightly harder. Well, we may have some other examples like, again, u is a function, depends on two variables, uxx plus u equals to 0. Okay? Then what is the solution to this differential equation, to this partial differential equation? How can we imagine?
Wait, so you're saying it's the second derivative on respect to x plus like the function equals to 0?
Yes. What can you say about it? Well, suppose u is only a function that depends on x. What is the solution?
Is this something going to be like the exponential of like minus ux and plus f of y or something like that? Or you can have.
So before that, what is the solution for this equation? If u is just a function in x, what is the solution to this one? Have you learned this in your ODE course or? Well, have you learned this kind of?
Since this is
like some oscillator.
Could you repeat that?
I think it looks like some oscillator.
Yes, it is. It is in your spring model, right? It is in your spring model. You try to oscillate. You try to stretch the spring and release it, and then it will oscillate, right? So this U should equals to A times cosine x plus B times sine x. Okay, and if you try to use, since this is a linear ODE, so you can also use well, the characteristic equation, right? If you use the method of characteristic equation, you find that it only have two imaginary roots, x equals to, well, or t equals to plus or minus I. So it must be A times e to the ix plus b times e to the minus ix. So you can try to change the coefficient and make it like this by Euler's formula. Okay, so similarly, as long as you know that the ODE solution, this ODE solution, the solution to this ODE, you can also make it the solution to the PDE. Okay, so this U is it can be written as, well, it can be written as A now is not a constant, B now is not a constant, so it's AY cosine x plus by sine x. Okay.
Oh, then a little question.
Mm-hmm.
It's
Sure.
like, so here basically your logic is, because we have some kind of a constant inside of this equation, we can just change the constants to some function of y. But how do we check that we didn't lose anything?
That's a very good point. That's a very good point. So how do we know that? Okay, from this example, it is quite clear that all the constant should be this, well, something depends on y. But for this one, it's not very clear that this is true, right? It's not just saying that, okay, since you have these two constants, so we just make them depends on y. Is that the end of the story? We just know that it is a solution, but is that all the solution? Well, this is a very interesting question. To answer this question, well, I don't know how you guys learn this characteristic equation to an ODE. By the way, this in general is not true, and in general we are not really interested in this kind of problems, which is really an ODE, but you change it to be a PDE. Okay, this is not well. I just show you several examples that seems to be easy. But in general, how can you know that this one has only this type of solution? Well, in order to answer this question, I hope you are able to understand this method of characteristic equation quite well. Okay, how do we understand this method of characteristic equation? That is, this 2 partial x. Well, you can try to think it is something like d over dx. You take it twice to acting on this u, right? And plus this u equals to 0, okay? Then for this one, you may try to write it in another way. You may try to see this guy as an operator. What is an operator? An operator is something that maps a function to a function, okay? Plus 1, which is a multiplier of 1, which also can be seen as an operator acting on u, okay? And then if you write this equation this way, what you can see is then we can do a factorization of this kind of thing, because whatever it is, it's just a square, okay? So that happens if and only if d over dx plus I d over dx minus I acting on u equals to 0. Okay. It is not very rigorous. Because you don't know what is an operator, but you can try to formally imagine this is true. So that means if you see this as a function g, then what we have is this operator acting on g equals to 0. Okay. So if this operator acting on g equals to 0, what we will have is d over dx plus I acting on some function equals to 0. Okay? And as long as we know g, we can do it again and solve u. Okay? So how can we solve this equation? Okay, this equation is not so hard to solve. It's just this first order linear equation. And what you can do is you can divide g both sides and take the integral, and this will become logarithm of g is equals to I. So which is why your g must equals to some constant times e to the ix. Minus ix. So in this case, if you try to do it for an equation that depends on y and x, then when you try to divide g and find the antiderivative both sides, what you will find is then this constant must be a constant in y. Okay?
That was a very beautiful magic, but like, how do we know that we can like treat derivatives like that?
As long as you know this operator's operation, you are able to do that, well, at least algebraically, right? Algebraically, this is true. It will give you this operator and this operator are the same, which is why you are, well, when in your ODE course, you try to learn this characteristic equation method, right? The main reason why characteristic equation method works is because of this. You can do it like that. By the way, this is something not in our course. Okay, this is just something that should be discussed in your ODE course. Again, this is just one example that will help you to understand what is the difference between ODE and PDE. Unfortunately, in this semester, we will not see a lot of this kind of examples as easy as ODE. Okay. Let me give you a last example about PDE. Okay. This example is also very important. We will soon see why it's important. Maybe next week. Okay. You have u, x, y, again, a function, and then what you have is now you really take two derivatives, both x and y, and it gives you 0. Now the question is, what would be the solution to this differential equation? It's still easy enough, right? What is a solution? What would be the general solution? You take derivative in x and then take derivative in y, then you got 0. Okay, then how can you solve it? What would be the first step?
Well, we can just do what you just did. We can write it as like d divided by d y multiplied by d divided by dx.
Yes,
and then
do that.
Oh, we don't have any. Oh, that's nice.
I think the problem here is while we are integrating, the order of x and y is matters because.
Oh, that's a very good point. Yes, well, in this course, for the sake of simplicity, okay, we always treat our function u to be continuous differentiable, okay? So which means uxy and uyx are always the same. We always assume our solution to be like that. Otherwise, the solution or the function are over too complicated for us to discuss.
But even if in that case, like if uxy is 0, then maybe by integrating with respect to y, I can get something like ux equal to f of x, and then it's an integration of f of x with u. But if I integration with respect to x in the beginning, I think the result is different. Or
the result could be different.
Or I think it could be the same, but of different forms. Like they can be equal to each other.
In the multivariable calculus, we actually study this theorem that if you have the conditions that we already assume when we solve this PDE, then they are equal.
Yeah, I know they are equal, but they are different in forms. You can try.
Well, they might different in forms, but we can write it in some very easy uniform forms, right? For instance, if you take the antiderivative in terms of y, then you get this ux, or you take partial x in u to be fx, okay? If you take the antiderivative again, then you will find, okay, you have to find the antiderivative of fx in terms of x, right? So let's say the antiderivative of f, little f, is capital F. Then I guess the form you want is done, right? Then you have to plus some constant in terms of x, let's say this one. So if you write this solution in this way, see, then, well, either you take the antiderivative in y or you take the antiderivative in x first, you get the same thing. It's just some trick about how to write it, okay? So you can see that this just tells us if you have uxy, this mixed derivative equals to 0 of your function, then that means you do not have this function, do not have a mixed term. It only has some terms that depends on x plus some terms depends on y. Okay, this is the only information this differential equation can tell us. Okay, so, well, these are just some examples about solving some really, really easy partial differential equation. Unfortunately, in this semester, you will find that those kind of things, almost everything we are able to solve. And we will not solve something that harder than this kind of PDE. Though, which also means that, okay, we are not going to solve a lot of PDEs. So let me write down the rigorous definition of a partial differential equation. Okay, because we don't really write the rigorous definition, although the rigorous definition is not quite important, but I still want to introduce to you because most of you are math major. An expression of the form, by the way, so U is in Rn, it's a domain, okay? And let's say U, we always assume U to be an open subset of Rn. Open subset of Rn, you can imagine it is, for instance, in R1, it's just an open interval, and R2, you can imagine it's just some kind of open balls, okay? And we have an expression like this, f dk ux dk minus 1 ux. This dk means you have some derivative and this derivative has a power of k.
Is that Jacobian?
You can think it's kind of a Jacobian. Yes, you can think it's a du is like well, ux1, ux2, and uxn. Like this. You take the partial x1, partial x2, partial xn, and if you take another d, that means you will have a lot of things. You will have, if you take another d, then that means you will have a lot of things. We don't really need to write it as a Jacobian. You can just write it as a vector. ux1, x1, ux1, x2, and so on. Okay, uxn, xn, and so on.
But d, sorry, so d changes the dimension of the vector in this sense, right? Or
yes, it will change. It will change the dimension because at the very beginning, your u is just a function, maps Rn to R1, right? But d means you will have a lot of derivatives. You collect all these derivatives. We just want to write it in a compact way, okay? No other reason. We just want to write it in a compact way, so that we don't really need to write this term to be ux1, x1, ux2, x2, ux3, x3. And instead of that, we write it like this, okay? And that means all the case derivative, all the case order derivative of u, all the case k minus 1's derivative of u, okay? And so on, and du and u and u and x equals to 0, okay? Where x, be careful, x is actually equals to x1, x2, x3, until xn, but we write it in a compact way. No other reason, okay? I don't want to write it as x1, x2, until xn. X is in Rn, okay? It's in this domain. Is called a case order PDE, where this f, well, I wrote it as some multivariable functions. This f is actually from Rn to the power k cross Rn to the power k minus 1 cross into Rn cross R cross U to R. Okay, is given. This is a way you try to write down the relation between all these kind of terms. It's just a function, okay? And U with domain capital U maps to R is unknown. Okay. And the solution U is a function that satisfies, let's say this is 1. Satisfy 1. At least for x in U. It doesn't matter what other x, but at least for x in U, it satisfies this equation. Okay? This is the definition of a partial differential equation. And we will introduce more, but let's have, well, it's kind of late. Let's have a 10 minutes break and we will resume at, well, 4:14, okay? Now feel free to do whatever you want. We have 10 minutes break.
Wait, so we were supposed to learn that kind of tricks with like differential that you did in the beginning in the ODE course?
Well, I just want to say that it's, well, all this kind of method in PDE, they will use some very, very basic things in ODE, like what I showed you before, okay? But no more than that. And most of the very tricky way in you have learned in your ODE course will not be useful in PDE, okay?
Because we didn't really like do this kind of things before, honestly. Like we were doing different things. Like
I know. Yeah, but it's okay. So the main method, okay, let's make it clear. The main method we are going to use this kind of antiderivative, okay? Antiderivative. Not even for this. Not even for this. The main method we are going to use antiderivative. Okay? So this basically all we need from ODE. But I think you must learn some tricks in your ODE course about how to solve a particular ODE, don't you? Otherwise, it will be very weird.
Well, in a sense, like for example, like we learned like the simple ones, like the f derivative equals f. That's just like e in the power of something, right? But that was like basically Professor Castinger's point was that like you don't really have to, like you can't really find the solutions all the time. So we didn't like, so we focused on
Wait, but I think you should learn this method of characteristic equation, right?
Yeah.
We did characteristic
systems.
And do you do this well integration factor, this kind of thing, or undetermined coefficient stuff?
Like we did integrate, but like very, very simply. Like we did like when you integrate a lot of times to approximate like a function, but it was a theoretical tool mostly. We didn't like use it in practice. Yeah.
So suppose I gave you well, let's see. Okay. Anyway, but whatever. That's enough for our course. Okay. I mean, not enough for you, but it's enough for our course.
What we learn is mostly about like autonomous equations.
Yeah, that's right. The autonomous equations, so that you can get some idea about dynamical system. That's for sure. But you still need some basic tricks about. Maybe in some other engineering course, you are going to learn this kind of thing. Yeah, I don't know. Yeah.
Yeah, I think there is no tricks for autonomous system because it's simple.
Not really. Yeah, it's not as simple as you thought. But
Okay.
well, but I think for linear, for instance, are you able to solve some problems like like this? Is that like you have this, well, here is not a constant. Are you able to solve it?
This is a non-autonomous one.
Okay. Okay, so yeah, then yes, you only learn this autonomic. Then okay, I got you. Yeah, that's fine.
So our mechanics is something like we simplify it to a planar system, like do substitutions like y equals to df dx, something like that.
I know. Yeah, this is a very well dynamical system course. But I think at least for some engineering students, they do need this kind of idea about how to solve some very basic ODE. Anyway, yeah. Anyway, it's not really necessary for math major, but yeah. Anyway.
Does anybody need a link for these two books? I have already bought them.
Wait, what did you say?
The link for these two books. I'll post it in our WeChat group.
Oh, you mean to like the free online book?
No, the hard copy, the physical book one, brought by the Chinese publisher.
You guys are so lucky. You can just like order books on Taobao.
Yeah.
Yeah, well, as long as you go to US, you'll find that the best thing in China is you can buy all the textbook very, very cheap, a very, very low price. It's almost 1/10, yeah. 1/10 of the price in US.
Yeah, if you look like the prices on like Amazon and you look with them on like in like Chinese currency, they actually like sometimes like the same or even like bigger numbers in USD.
Yes, yes, definitely, yes. Well, yeah, I think for this book, yeah, anyway, so which is why I would recommend you to buy some math books that published in China. That makes life much easier.
Oh, before going to US, we can just like buy a lot of books from China and then just like go with them to US. So
This is what I did. I think I just sent like 30 books from China to US. Yeah, when I went to US, and when I go back to China, I only take like 10 books.
Because are the 20
for the rest book, I can buy it from in China very easily.
Oh, nice.
Okay, I think we should start now. By the way, so I'm not pretty sure, but are you familiar with the notation I used about this partial derivative, like this kind of notation? Are you familiar with this partial x and partial y, for instance, partial x, partial y, this kind of notation? Is that okay for everybody? I mean, have you learned that in your Calculus 2 class?
I think, yeah, we did it in multivariable calculus.
Okay, then that's good. Yeah, okay, so because we will use this kind of notation a lot, and maybe also even with this notation a lot. Okay, this du or the gradient of u a lot. Okay, gradient of u is the same as du. Okay, it's ux1, ux2, or ux1, ux2, ux3, and so on. Okay, and talking about this, well, differential equation, you can see that, by the way. So for the previous examples, this partial differential equations, this one and this one and this one, they are both second order differential equations. Okay, here let me show you more examples about differential equations. Okay, when do we start? Okay, yeah, we do have plenty of time. So let me show you more examples about a partial differential equation. Those are very famous partial differential equations, and they all have a name. Okay, they all have a name, so that you can see why I say partial differential equation is much harder, because there is no general way to solve them in some general theory. You have to learn them one by one. Okay, let's see this one, some examples. Ux, for instance, ux plus uy equals to 0. This is a very easy first order differential equation. We are going to learn it this week or next week. Okay, this is so-called the transport equation. Which is a very useful differential equation, and also the structure of this differential equation is quite easy. Okay, it's one of the most basic differential equation. And well, you may change this well, coefficient a little bit, but it's still first order differential equation. And this is also a transport equation, but here this coefficient may depend on y. Okay, it may also depend on x, it may depend on whatever, but this is still a transport equation. But if you change this coefficient more, if you change it to be function u, not a variable, then this guy, it has a different name. And it's also totally different from the transport equation. Its property will be different. The reason why it's different is something we will discuss in 5 minutes. Is this differential equation is not a linear differential equation. Okay, it's not a really linear differential equation. So this equation, somebody call it a shock wave equation, or well, I think most people in my area call it Burger's equation. I think Burger's is a name. It's not real burgers. Okay, it's very important, and well, people even now people are trying to study it, even though you think it's very easy, just first order. It's quite similar to this one, but even right now, currently, people are studying it. Okay, we still have something unknown to study, and well, another equation is also a very important equation. It's uxx plus uyy, which is partial u, partial ux twice, partial uy twice, and equals to 0. Or in some other notation, if you take all this kind of second order derivative without the mixing term, we call it a Laplacian u. Okay, Laplacian u equals to 0. We use a triangle u equals to 0. Okay, this is also very, very important. It's one of the most basic type of differential equation. It's so-called the Laplace equation. Or somebody calls it an elliptic equation, or somebody calls this u a harmonic function. Or this, someone also call it harmonic equation. Because it's very symmetric and it's very harmonic in some sense. Okay, not really like that, but you can try to imagine it's like that.
Wait, sorry, you said the change in u equals to 0. What did it mean again?
This one? Or this one? Which one?
Yeah, the one in the brackets.
Oh, this one. This just means this, okay? So Laplacian, you can think it like, if you know the notation of Jacobian, it's like the trees of the Jacobian acting on a function, okay? Acting on multivariable functions, okay? What is a Jacobian of a function? The Jacobian of a function is just a matrix, so that the first term is a partial x1, partial x1, partial x2, 1, x2, partial x1, x3, and so on. Okay, this matrix. If you take the trees, what you get is so-called the Laplacian. We use this notation to denote it. Okay.
So it works for like more than 2 dimensions, right?
Yes, it works for any dimension. Okay. For any dimension, we can always call this kind of function to be a harmonic function, and call this equation to be Laplace equation or harmonic equation. This is very, very important, and we will discuss something more in this semester. Although it looks like it is, if you have the second order differential equation, second order partial differential equation, it cannot be easier than this one, okay? But it's still not so easy. And another example is, this is so-called the heat equation, which you will see why we call it the heat equation. Suppose, you have this kind of thing, okay? This is so-called the heat equation.
What is u with respect to t?
Well, this Laplacian is respect to not t, yes. U is equals to u t x. And this Laplace is Laplace in terms of x. Okay? So this is so-called the heat equation. Okay? And it describes the, heat, the temperature distribution of a heat conduction process. We will introduce this equation very soon, okay? Hopefully we can do it today. And there is another kind of equation, which is also very important. That is, you change this ut to be utt, which equals to Laplace u, okay? Somebody called this operator, partial tt minus Laplacian, to be a square. But if you're not really in this area, then probably you do not really want to use this notation, okay? This is a very, this is only the notation that for people who are in this wave equation, this dispersive equations area. Well, for people like me, I don't really want to use this notation, okay? This is so-called a wave equation. Again, u is u in t, which we always use t to represent time and space, okay? And Laplacian is, you only take Laplacian with respect to space, not time, okay? This is something very, very important. There's three kind of three different kind of second order differential equations. They look very simple, but they have a lot of very good properties we are able to study. And in this semester, we are going to study basically this kind of equation, which is first order differential equation, and this, which is Laplace equation, and this, heat equation, and wave equation. Those are the equations we are going to learn in this semester. I cannot guarantee we are able to learn all of them, but we can try, okay? So you can see that, again, PDE is much harder even though you don't have any trick on your differential equation, okay? For instance, you don't have any trick. I mean, for instance, if you change here by 1 and 1 to be 1, 2, maybe it's still able to using the method we are using now to deal with it. But if you change here to be something like X or Y, then the method we are going to learn in this method may not work, okay? And also, some other type of differential equations, for instance, if you study the quantum mechanics, then it is very important to know the Schrodinger equation, okay? But the Schrodinger equation is mainly about, well, it's mainly this type of equation. It's ut minus I uxx, or ut equals to I Laplacian u. Okay, so you can see that even though sometimes you just change this constant from 1 to I, then you may have some different property. This is so-called, well, this is not really the Schrodinger equation, that is the key part of Schrodinger equation. So let's say it's useful in the quantum mechanics. Okay, and then some different types of well, differential equation. By the way, so this is a differential equation in quantum mechanics. It looks like this heat equation. However, for people study this differential equation, like the Schrodinger equation, it may use mainly it will use this kind of differential equation, the wave equations method. Okay. And also maybe some other differential equations like this one, ut plus ux plus uxxx equals to 0. This equation is mainly for those people who study the wave equation. This is so-called a dispersive wave. Okay, and another type of equation is well, you may have a wave equation, and you may have something like uq. This is something like nonlinear term. And then we cut this into two parts. And this part you can somehow think is like a perturbation. But this is, again, another type of differential equation. And it's you may use some idea from this, but it's different. Okay, this is wave with some interaction. This uq can be seen as the interaction between the particles, or it can be seen as the reaction of some, well, creature or whatever. Okay. So this are basically the differential equations you can see in the future. Probably you will not be able to see those kind of differential equations because they are over too complicated. Okay, and if you are interested in the differential equation, you can try to learn this type of differential equation by yourself. But well, if you want to, then well, those are all very complicated differential equations. Okay, but they are also very useful in the physical science. Okay. Okay. But in our course, we are only going to learn 4 types of differential equation. Linear, well, this first order one, and this harmonic equation or the Laplace equation, the heat equation, and the wave equation. Okay. So, as I mentioned before, we say that the equation we have at this moment, for instance, the Laplace equation, heat equation, and wave equation, or this transport equation are all easy, at least easier. But for those kind of equations, for instance, this one, or this one, it's a little bit harder. The reason why we say that is because, well, all this kind of equation that we are treated as easier equation are some equations so-called the linear equation. Okay? The so-called the linearity, or the linearity. What is a linearity, or what is a linear differential equation? A linear differential equation is, we can write the equation in the form LU equals to 0, where L, again, is an operator. An operator means L, well, V is a function, and LV is a new function. Okay, so which means L, you can see L as a map, and this maps a function to a function. Okay, for instance, L could be partial x. You take the derivative in terms of x. Or L could be Laplace, right? You take partial x, partial y. Or L could be, A times partial x plus B times partial y. Then this can also acting on a function. Or L could be something like, L could be an operator so that LV equals to V squared. So this is still an operator, right? And the rules here, the rule for L is to just multiply this function by itself. Okay, then this kind of thing is also called an operator, right? Or LV is partial t plus this V times partial xv. Okay, this could also be seen as an operator. And we see L is linear if it is like a linear transformation in your linear algebra course. Okay, LU plus V is equals to LU plus LV. And LC times U is equals to C times LU. For any UV functions, C constant. Okay, it's just like a matrix. Okay, it's just like a matrix acting on some vectors, so that it is you can break it. If you have two, you can break them, and if you have a multiplication by constant, you can take it out. Okay, and this LU equals to 0 is linear if L is linear. Okay. Any question?
I have a question about the transport equation. Like the coefficient of Uy, can it be something else? Like other than 1 or 1?
Yes, you can. It can be 3, it can be x, it can be whatever function you want. Okay, it can be anything. We always call it a transport equation, but this function really depends on U, then it may have some different properties. Okay, so we call it a Burger's equation.
Okay, thank you.
Sorry, what do we call an operator? Like, what's the proper definition of an operator?
Well, since you don't really, you guys don't really know what is a function space, so I am not able to give you the rigorous definition of an operator. So right now, what you can imagine is, well, an operator is just something, it's just like a map, so that you give me a function, and this map will map this function to another function. Okay? But of course, this is not a good definition because if I give you a map, then I have to tell you what is a domain, what is a range. But I'm not able to tell you what is a range, what is a domain of this operator as a map. So, which means you can only imagine it is a map, okay? But basically, it's just like the rules. It's just like the rules how you play with your function. Okay, like an operator can be seen as this one, so that LV is you take A times this V take partial X, and B times this V takes partial Y. Okay, just like how you play with your function. And if the way you play with your function is linear, then we call it a linear operator. For instance, you can see that these two guys are linear, right? Because if you're acting on U plus V, then you can break it. If you're acting on U plus V, you can break it. So does this one. This is also a linear operator. Okay? But this one is not a linear operator because LU plus V is U plus V squared. Right? And this one is not a linear operator because LU plus V is where you have U plus V times partial X U plus V here. So you cannot break it. If you have some terms like V squared, like this V dot, V times partial X partial V, then this operator cannot be seen as linear. Okay? And in our case, it is actually much easier to classify what is linear operators, okay, or what is a linear partial differential equations. We can actually list them, okay? We can list them and then say what is our linear partial differential equation. I'll just list them a little bit later, but at this moment, let's see why a linear operator or a linear partial differential equation is easier for us to study, okay? Well, since you want to have something like linear, so you may see that it's actually something came from this linear algebra, right? So maybe you can try to get some information or get some benefit from the knowledge of linear algebra, okay? Which is, for instance, we can define LU equals to G, and if G not equals to 0, it can be called, L linear. And if G, you have something not 0 on the right-hand side, we can call it an inhomogeneous linear equation. If G equals to 0, it is a homogeneous linear equation, okay? And in linear algebra, we know that, the reason why we're interested in this linear equation or inhomogeneous linear equation or homogeneous linear equation is simply because it can help us to solve it easily. It can help us to find all the solutions, right? And here it's actually the same, but the little bit different is it can only help us to find more solutions, but it may not be able to help us to find all the solutions of a partial differential equation. The good thing here about linearity is, okay, if U1, U2, and Un are solutions to LU equals to 0, so does the summation or the linear combination of them, right? So which means as long as you find zero solutions, you're able to find a lot of solutions. But it is different from linear algebra because in linear algebra, you know that, okay, as long as you can find a, well, big enough set of solutions, you are able to do the linear combination and find all the solutions. That depends on the dimension of your operators. It depends on the dimension of your vectors. But here, this is not, again, some matrix, and this is not, again, some vectors. This is something like infinite dimension. So which means this way may not help you to find all the solutions. Okay, but sometimes it does help. At least it can help you to find a lot of solutions. And similarly, well, you can also, this is in linear algebra, this is so-called the superposition principle. And here we also call it superposition principle. And you can always, for the homogeneous and inhomogeneous problem, you can always add the solution to the homogeneous problem to a solution, a special solution to the inhomogeneous problem, okay? Is a solution to inhomogeneous problem. And this is actually good enough for us. This means in order to find a solution, the general solution to the inhomogeneous problem, you can only find one special solution and then add the general solution to the homogeneous problem, okay? This in general is true. Because for any two of the solution of the inhomogeneous problem, you subtract them, then you got a solution to the homogeneous problem, right? So this would be useful. Okay, this is why we are interested in this linear problems, okay? Because linear problem, somehow it is kind of simpler than the nonlinear problems. Now let me just list all this kind of linear problems for you, okay? Or possible linear problems for you. For instance, well, a PDE is called linear if it has the form summation of all this index alpha less or equal than k, a alpha, where alpha equals to alpha 1, alpha 2, until alpha n, okay? A alpha x is the corresponding coefficient, d alpha u, okay? Equals to fx. Alpha is equals to alpha 1, alpha 2, and alpha n is in this zn plus to, well, z plus to the power n. They are positive integers. And d alpha, well, it's just a notation, is d alpha 1, x1 alpha 1, d x2 alpha 2, and so on, d xn alpha n, okay? So this means for all the derivative of u, the coefficients are only something that does not depend on u, okay? In this case, it is linear. Other than this case, you cannot really say it is a linear equation, right? For instance, if the coefficient in front is something depends on u, then you cannot really say it is a linear equation, right? Because the operator is not linear. Okay, and then if it is not linear, there are some cases such that it's not so complicated, just like our Burger's equation. Okay, just like our Burger's equation, it's harder than the linear equations, but it's not as hard as something more complicated. This kind of thing, we call it semi-linear and quasi-linear. Okay, a PDE is semi-linear if it has the form like this: alpha equals to k. Okay, by the way, this absolute value of alpha is equals to alpha 1 plus alpha 2 plus alpha n. Okay, just the notation. And the index is equals to k, where k is the highest power of your PDE. Okay, highest order of your PDE. And a alpha x d alpha u, which means for the highest order of your PDE, the coefficient adjusts something that does not depend on u, plus something that may depend on everything, but is only something of lower order. Okay, du ux equals to 0. Okay, this kind of differential equation is so-called the semi-linear differential equation. For instance, the so-called the dispersive, the wave with interactions equation, right? Which is a wave equation plus some terms that are not so good, which is u cubed. It's not linear, but the highest order of derivative is linear. Then this kind of equation is semi-linear. It's better than those equations such that in front of this kind of thing, you have something nonlinear. It's easier than that. Okay, to do analysis on this kind of differential equation is easier. At least easier. It's harder than the linear one, but it's easier than, well, you have something in front to be something not so good. And this type of equation, it will always be somehow have the same or similar properties with this guy. Okay, so this can be seen as lower order term in some sense. We may be able to see this kind of differential equation in the future. And another type of differential equation is so-called the quasi-linear differential equation. If, well, it has a form summation of, again, alpha equals to k, okay? A alpha, the coefficient, now it does not depend only on x. It may depend on u, okay? But the good part is it depends only on the lower order derivative of u. The, well, k minus 1 u and du ux plus something, well, you can see that, so for instance, if in this differential equation, we times u here, or times ux or ut here in front of utt and uxx, then it's from a semi-linear to a quasi-linear differential equation, okay? But it's still somehow linear because the highest term is still can only interact or have the coefficient like something of lower order. Okay, if it is something of lower order, then it's somehow easier than if something depends on the higher order. Okay, probably we will not have time to discuss some more examples about quasi-linear differential equations. well, probably we are able to because, I'm sorry, probably we are able to discuss because we are going to discuss the Burger's equation, right? The Burger's equation is a very good example. The Burger's equation is a very good example as a quasi-linear differential equation, right? You see, it is quasi-linear because in front of it, it has some coefficient that depends on the lower order derivative of this solution, of this function. Okay? And lastly, well, the last case is if it is it is something that is nonlinear, totally nonlinear. If it is something that totally nonlinear, is fully nonlinear, if it depends nonlinearly upon, well, on the highest order derivative. For instance, very few people are able to study the fully nonlinear differential equations because it's very hard. For instance, suppose you have UTT square equals to UXX, right? This would be a fully nonlinear differential equation. And the property of this differential equation, partial differential equation, would be hard to study. Okay. Any question? Any question?
I wonder. So, like for example, the absolute in the type 1, like a PDE is linear, and alpha is the absolute value of alpha is smaller than k. In this case, does it mean like every combination of alpha 1 to alpha n, that is their sum is smaller than k, should be counted in that? Does it mean that, or there is a certain type of?
Well, it depends. Some of the A alpha x could be 0, right? So for instance, well, uxx plus uyy equals to 0. Okay, you can write it this way, and then your A11 x equals to 1, right? A12 x equals to well, xy equals to 0. A22 xy equals to 1. Okay, A21 xy equals to 0. Okay, these are the coefficients, and this coefficient could be some constant, could be 0, could be something depends on x. Okay, did that answer your question?
Oh, I think I understand it now.
Okay, so why we write it this way is simply because sometimes if you, especially when you study this kind of this Laplace equation, then the coefficient can somehow form some matrix. Okay, it may form some matrix, and then sometimes we are interested about the coefficient matrix. So which is why we write it in this way. Okay. Any other question?
Yes, I am a little confused by the form A alpha x D alpha u. Can you give me more examples, like to show what it is like?
Which one? This one? This notation?
The form A alpha x D alpha u. Yes.
Oh, this one. Okay.
Yeah, I'm a little confused what it is.
Yeah, of course. So for instance, like in our, for instance, in our UTT minus UXX equals to 0, okay? In this differential equation. How can we write it in this way? Well, we can write it in this way by saying that, okay, you have t comma x. There are two things here, right? So you are in R2, two-dimensional space. And then your alpha could equals to what? Well, your alpha could equals to is 1 here and 0 here, or 0, 1, or 1, 1. Or, well, I mean 0, 0. Okay? Or is 2, 1, or is 1, 2, or is 0, 2, or is 2, 0, right? Or is 2, 2. Yeah, I think that's or something else, okay? Or something else. A lot of things. So which means alpha is in z plus square. Your n now equals to square. N equals to 2. Okay? Now, your differential equation of order k. The differential equation of order k can be written as the summation of alpha is less or equal than k. For instance, we know that this differential equation is of order 2. Okay, it's of order 2. So which means we want alpha to be less or equal than 2, a alpha x times, well, we know that it's linear, d alpha u equals to 0. Okay, this is what we want to write it as. But now this x is it's a vector. It's actually equals to t comma x. Okay, and if you want this alpha to be less or equal than 2, you see that alpha is equals to something like m comma n. If you want m plus n is less or equal than 2, then that means alpha could equals to, okay, 0, 2, or 2, 0, right? Or 1, 1, or 1, 0, or 0, 1, or 0, 0. It cannot be something else, right? It cannot be other than this 1, 2, 3, 4, 5, 6. 6 numbers. 6 tuple of numbers, right? So then what does that mean? That simply means if you want to take d alpha u, let's see what we have if we plug in here, okay? D alpha u is equals to, okay, if alpha is 0, 2, then that means you take the first variable, which is t, derivative 0 times, the second variable, derivative of x, 2 times of u. Okay, so this is, well, partial x square of u, okay, or uxx. So this is when alpha equals to 0, 2. So that means a 0, 2 of x is equals to, if you wanted to match our differential equation, it should equals to -1. Okay? And then what if alpha equals to 2, 0? Alpha equals to 2, 0 is dt2 dx0, and which is partial square, partial t square, u is utt. If you wanted to match our differential equation, then that means a 2, 0 x should equals to 1. Okay? And similarly, if you have some other alpha, it's still like d alpha 1, whichever it is, t d alpha 2 x acting on u. Okay? And we know that this differential equation has only these 2 terms. So we know that all the other coefficients, a alpha x, should equals to 0. Okay? So we write it in this way. We write this differential equation in this way. Okay? It's just some compact way to write it. Nothing more than that. Because we want to, yeah, because we want to write it in general. We want to state it in general. Okay?
Okay, thank you.
Any other question? So before we go to the four fundamental type of, or four basic type of differential equation, partial differential equation, let me write down several remarks about, well, about the differential equations, okay? Several remarks about, well, some basic requirements or the preliminary knowledge that I will assume you know in this course, okay? The first one is, well, this is just a remark. This is, well, the derivative are always local, okay? So if you write down a differential equation, it always means that, okay, you take the derivative of this function at some point, and then plus this this function at this such point equals to 0, okay? So every derivative or whatever, you have to think it as the derivative of these functions, and it's not the whole thing, it's not the whole picture. Every PDE is just a local proposition, okay? You don't have any non-local property. You could add some non-local operators, but then this makes problem much, much harder, okay? So the derivative in this course are always local, are always point by point derivative, okay? And as we discussed before, the mixed derivative are equal. So we always assume that uxy equals to uyx. We always assume that our solution are pretty nice, are smooth. Okay, you can take derivative infinite many times. Okay, and thirdly, well, if you want to learn this partial differential equation, again, this is analysis course or advanced calculus course, you must be very familiar with the chain rule. Okay, and you better know, although this is not really necessary, but you better know the green theorems and well, divergence theorems and maybe Strauss theorems, Strauss formula, which are the basic stuff, like, well, the integration by parts of higher dimension, okay? The integration by parts for multivariable calculus. I hope you are able to know that, but if you don't know that, it's also fine. But knowing that, you are able to get a better intuition about how we can deal with partial differential equation, okay? And also, I hope you are able to know, still 3. I hope you are familiar with, since we are going to discuss about the Fourier analysis, the very basic stuff of Fourier analysis would be the Fourier series. So I would like you to know a bit more, or at least be familiar with the infinite series of functions and the derivative of this kind of series. Like Taylor's expansion, but Taylor's expansion is not useful in terms of partial differential equation. It's very hard for you to find something that converges uniformly. So, which is why we have to introduce this kind of, well, Fourier analysis, Fourier sequence, okay? And the derivative or integration of this kind of sequence of the series, okay? And you will also need to know, this is something very necessary when you try to learn this first order differential equation, which is so-called a directional derivative. which is how you can take the derivative. You know how to take derivative for multivariable functions, but how can you take the derivative from one direction, right? Well, that's not so hard, right? If you take the if you want to take the derivative along this vector v, this v direction, then that simply means you take the gradient of u and times v, right? This is a derivative with respect to this v direction, okay? Or the gradient of the gradient of u, you multiply by v, okay? Just the same, just a different notation. And well, and also maybe some very easy ODEs. Like how can you solve this uxx equals to 0, uyy equals to f, or uxy equals to 0? This kind of ODEs. I hope you are able to know it, but not very fancy, not at all, okay? These are the basic things we are going to use, and I hope you know for this session, for this course. Okay? Any question? Any question?
Can you explain about the derivatives are always local, the first term?
Well, the derivative always local is, well, you have to think the partial differential equation not to be something like, well, something like you always have an explicit solution, okay? You better think it just tells you some kind of property of a function at some point, okay? For instance, you know that, well, this kind of differential equation, right? It's an ODE, maybe I should say D instead of partial. It's an ODE. But if you try to understand it, maybe one way is you know that, okay, u is an exponential function, then, okay, it satisfies this equation. This is how you understand it globally. But the way you try to treat it locally is just like you treat it as a dynamical system. That is the idea. You try to see, okay, so this differential equation just tells you at each local point, at each point x, well, the derivative of u is equals to minus u. Okay, this is how you treat this kind of differential equation locally, not globally, not what is a solution curve, but you can see that this differential equation just tell you at one point what happened. Okay.
So is it like, because a derivative at one point, I can think of them as numerical, like numbers, something like that.
Yes. And well, you can just think this PDE just tell you some properties of each point by point very locally, very small neighborhood of that point.
Okay, thank you.
Not really see, okay, it tells you some global property. This is sometimes confusing, but I believe if you see more about the, well, differential equations, partial differential equations, you will see why I say that. Okay. Any other question? Any question? Okay. Since we only have like 20 minutes, so maybe I'll just start to tell you how we can get these 4 important types of partial differential equation. Okay. Let me just give a start of this. Well, again, what are the 4 important types of PDEs? As we mentioned, the first one is well, the transport equation. Something like ut plus b, where b could depend on x, could depend on u, could be anything. du equals to 0. But it is just a first order differential equation. first order partial differential equation. For instance, well, if it is in one dimension, then we don't really need to write it as b. So it's ut plus some function times ux equals to 0. Okay? And the Laplace equation, which is Laplace u equals to 0. Okay? And the heat equation, which is ut minus Laplace u equals to 0. Okay? The wave equation, which is utt minus Laplace u equals to 0. Okay?
Oh, by the way, I have a question about the heat equation, because I remember what we've done before is like u of t is equal to like u x of x, something like that. But isn't the Laplace of u like u tt plus u xx or something like that?
Well, again, this Laplace, okay, this Laplace is only the Laplacian in terms of this spatial variable, which I'll tell you why we call it a spatial variable. If we write something like t here, then in our PDE course, we almost always means it's about time. Okay, every PDE, remember, every PDE is a story. And then the thing is, when you try to solve a PDE, you try to tell what the story tells you. And you have to be able to say the story. And one basic thing about this kind of story is you, in these stories, you may have different, well, you may represent different quantities. But the variables t and x, maybe y, z, x, y, z always means the space coordinate. And t always means the time, okay? So here, this Laplacian is always Laplacian in terms of x, okay? No more, well, no more than x. If you involve one additional variable like t, then you just put it outside, okay? So it means for instance, in two-dimensional, if you only have tx, then the heat equation would be ut equals to uxx. Okay, and the Laplace equation, well, there's no Laplace equation because Laplace equation does not involve t, and the wave equation is utt is uxx. Okay, but in general, this Laplacian of u is just a uxx plus uyy plus uzz. Okay, whenever we write it, it will never have this. Okay, if we write it this way. Okay. Any other question? Any other question? So let's first see why we call this the transport equation and where does it come from, okay? Well, let's first try to see the easiest case, okay? For instance, b is a constant. Suppose b is a constant. And suppose we are in dimension 1, okay, so, or dimension 2. You only have t, x. Then your differential equation can be written as b times ux equals to 0. B is just a constant, nothing more. Since this is constant, so let's use c instead of it. To make it clear. Okay, so then if this is the case, maybe first we can try to look at it and say, okay, what does this equation tell us? For instance, if you know that ux equals to 0, then this equation simply tells us, okay, this u shouldn't depend on x, right? This is what this equation tells us. Or if you find that, okay, uxx equals to 0, then that means, okay, if you take the ux doesn't depend on x, right? And so on. And this u should be a linear function of x. Then the question is, if you have this kind of differential equation, what does it tell us? What's the meaning of this differential equation?
The dependence of t and x are of same order. You mean something like that?
Yeah, they are of the same order. That's true. But what do you mean by order?
Wait, sorry for interrupting, but like, why do we have that the solution would be ut plus cux equals to 0? Wouldn't t or c be some kind of like function of t?
Well, we are not discussing about the solution, okay? At this moment, we just look at this differential equation. I'm not going to solve it. I just want to know, what does this differential equation, what's the story of this differential equation? What does it try to tell us?
Since we are treating these equations numerically, so I think it's that the rate of increasing or decreasing rate, they are with respect to different variables, they are similar, or they are dependent linearly, like with a multiple of c.
Yes, that could be one explanation. Any other idea?
Well, they are proportional, as Lancelot said, and basically that means that probably our functions would have like kind of the same shape, and like in a sense of like when one is positive, another should either be positive or negative. So yeah,
that's possible. That's possible. But well, now let's try to take another look at this one. Okay. So if you do have this kind of, this form without equals to 0, if you have this kind of form, what can we imagine? How can you get this kind of form? You see, it is like 1, c, okay, times ut, ux. What's this?
well, do you mean that if we take this solution and add it to any other solution, it will produce another solution?
It is linear. It is linear. That's true. But what does it mean? I mean, how can you understand it physically or geometrically?
Perpendicular to the vector 1c.
Yes, that's right. So that means if you go along this direction, right? If you take the derivative along this direction, if you take the derivative, directional derivative, it is actually 0, right? So which means the value of these functions does not change on this direction, right? So if you draw the picture, this is t, this is x, then that means, well, this function or the solution will have the same value along each of these kind of lines. These lines are just to have direction 1, c. Okay? So this function will have the same value along these lines.
Like the level curves.
It's more or less like a level. Yeah, the level set of this function adjust this straight line. Okay. So what does that mean then? Well, this is why we call it the transport equation. Okay. Suppose let's see on this x-axis. That means if you try to see this time t to be, well, this t to be time, then we can try to treat this u as a concentration of whatever stuff you have. Okay. For instance, you may try to trick some bullet, and you put this bullet on this x-axis. Okay. You put one here, maybe two here, and one here, and two here. Okay. Now, then the u equals to 1 here, 2 here, 1 here, 1 here. Let's suppose it is something like that. It's a concentration of your bullet. Then what happens is, as time goes, well, you try to push all your bullets on the direction 1, c, right? So after 1 second, what happens is, okay, you still have 1 bullet here, 1 bullet here, 2 bullets here, and 1 bullet here. Okay, but it, on the x direction, it moves. In 1 second, it moves let's say c meters. Okay, so which means you try to push all this kind of stuff, whatever it is, the bullet, the particles, you try to push them in one direction, in this direction, in this, well, positive direction on x-axis at speed c meters per second. Which is why we call it the transport equation. Because you try to do a transportation of this, for instance, this is x-axis. You have 2 bullets here, 1 bullet here, 1 bullet here, 1 bullet here, and you try to push them, okay? This u satisfy this equation means you try to push them, and after 1 second, well, it will move to c meters, and will move c meters, so that means 1 bullet here, 1 bullet here, 2 bullet here, and 1 bullet here. 1 particle here, 1 particle here, 2 particle here, and 1 particle here. Okay, this is why we call it the transport equation. Okay, so in physics, this is quite understandable, I believe. And it is quite useful in physics. It just tells you how amount of amount of material, or amount of, for instance, a coolant, or amount of waters. How does this amount of waters move? We will see in another way in a minute. Okay, after we make this kind of thing slightly more complicated. Is that okay? Is that okay for this? How this particle moves based on this differential equation? Any question?
Yeah, actually a couple. So basically we established that like the ux derivative is orthogonal to 1c vector. And so we have drawn like the vectors 1c. And basically we're saying because the derivative is orthogonal to those lines. But like, how do you make?
So which means along this line, well, this derivative must be perpendicular to this line. So that means along this line, it must be the same, right? These lines are the level set of this equation, right? Of this function. Okay. So which means this part of particles or whatever, it should move along these lines. It should move along this 1c, this direction. Any other question?
Wait, I am also confused by the 1c. Like, why do you define like this? I mean, 1 second, 3 meters in the direction. I don't see it. Like, how do you build the relationship between ut and ux and the time and the meters they go?
Well, first, this equation, if we don't say anything about this equation, we just can see from this equation that for this function, for this just for a function, okay, at this moment, we don't have t, we don't have x, we don't have this, the meaning of variables. We just know that this differential equation, it tells us, okay, your u must satisfy this equation. That means your u, another way to state this equation is, your u should be along each direction 1, c. Because you take the directional derivative. Along this direction, your u shouldn't change. Right? This is how we understand it as a differential equation. But then, if we try to make some physical meaning of this differential equation, we can say that, okay, this u could be the, well, could be the concentration of particles. And t could be time, x to be the position, okay? Then, if you treat it like that, then what happens is, this differential equation just to tell you how this particle will move, okay? So that this differential equation really have a physical background. At the very beginning, it's just a purely mathematical stuff. But then, if we make correct, if we make the variables correct name, then it will have the physical background.
Yeah, yes, I understand this, but I can't. It seems confusing for me to think of 1 second and 3 meters. Like when we go to 6 part, I am confused.
Which one? Which part?
1 second and 3 meters. Like they move.
Yes. Well, you can just imagine, okay, after you move 1 second, so which means you move t, you move 1 unit on the t direction, right? Then that means you move c unit on x direction. Okay, because that's well, that's what direction means.
But is there perpendicular? I think so. Why we go from 1 c instead of c -1?
Which one perpendicular? I mean, if you have the vectors direction to be 1c, right? 1, c. Then that means at, well, if you go m, if you use m multiply it, then it's equals to m, cm, right? So that means for any m unit on t direction, it's actually cm, it will move cm unit on x direction, right? And yes, it is perpendicular to this one, so that this times this equals to 0. So which means if perpendicular to this one, so which means if you go perpendicularly, then this u could change. But if you go parallelly, this u doesn't change.
Oh, I see. That makes sense. Thank you.
Any other question? And similarly, well, we can also choose B to be something not so easy, right? We can choose B to be something like X, for instance. If you choose B to be something like X, then the problem becomes this. But then how can we treat this problem somehow similar to this problem? Now,
sorry. I'm not confused why the U does not change. I think it may change proportionally.
Yes.
Like, okay.
It may change perpendicular in this direction. It will change, definitely. But it will not change in this direction. For any, well, you can just imagine this is like the level set of U, right? This is just like the level set of U.
I see.
Right?
Thank you.
So now B equals to X. I'm sorry, yeah. So we are slightly out of time, but let me finish this part. If you assume B equals to X, okay? And then you have this differential equation. Then how can we read this differential equation?
Like we just do the same thing. We get 1x is orthogonal to the derivative.
Yes, but what does that mean? 1x times ux equals to 0.
This time, I think we what the first thing we want to do is fix x to some special value.
Yes, for fixed x, yes, for fixed x is actually we're perpendicular to that. Then what does that mean? What does that mean?
Basically, it's like drawing the level sets, but now instead of like being lines, those level sets are functions, which functions. Are
exactly. This level set now is not a straight line; it's just a function. How can we find those functions? How can we find the level set in this sense? Well, suppose we have level set to be TS XS, right? This is a level set. That means if you take the derivative, it should give you 0.
Yeah, so I think it's like if we before had like 1c gave us a line, then 1x probably give us something like an exponent.
Yes, probably yes, right? So which is you try to take derivative and use a chain rule, right? So this is t prime u t plus x prime u x equals to 0, right? You want this guy to be this guy so that you find the level set, the curve of level set. So that means you want t prime equals to 0, well, equals to 1, and x prime equals to x. So that means you are along the curve x equals to e to the t, or c times e to the t. So the level set should be something like this, right? Now this is still a transport equation, but it may make those kind of particles somehow separate a little bit. Okay, but whatever, it just tell you a physical story about well how you can move everything to some other places. I think we don't have any more time on it. Next time we will discuss why we are interested or why we call those 3 other type of differential equations to be wave and heat and Laplace equation or harmonic equation, okay? And how we can get them, what kind of story they are going to tell us, okay? What kind of physical intuition they are. So I think I'll see you on Thursday, and I will be here until 6 o'clock, okay? If you do not have any questions, feel free to call.